It's a great pleasure to introduce Alyosha Efros, which, since you're in Unsupervised learning class, you've seen already many of his works. Alyosha is pioneer of unsupervised learning from before it was even remotely cool. It's called just, it was graphics still.
Yeah.
Vision and graphics.
Yeah. Yeah.
And there's been actually a lot of results we've been showing today and in previous lectures are actually out of Alyosha's group. And so it's a great pleasure to have you here today with us. Please join me in welcoming Alyosha.
All right. All right, folks. So I'm, since it's, second part of an evening class, I'm not going to stress your mental capacities too much. This is designed to be entertaining. So hopefully you'll be entertained. It's also, since you guys already covered a bunch of material from my group, I thought I would give you a little bit of kind of the intuitions and kind of a reasoning behind at least my road towards unsupervised learning. And so hopefully that will that'll give you a little bit more insight, and then at the end I'll show some of our stuff, some oldies and some newies, but we can go through them fast since I think some of them you already have seen, and so we don't have to go to the end. So please do ask questions. This is meant to be interactive. Okay. The title slide. This is something that that came out of the. We had an ICCV conference in Chile. And they have this great tradition of having lots of murals. And so I was walking around before my workshop, checking out murals in Santiago, and I took a picture of this particular one, and then I was supposed to give a talk in one of those vision workshops, and I thought, this is a perfect mural. I just need to have a right title for it, and I was talking about unsupervised learning, and I thought, this is great, The revolution will not be supervised. And this is a play on an old 60s song, The Revolution Will Not Be Televised. And then Jan LeCun was sitting in the front row of this workshop, and he really liked this. And so then he took off this title, and once Jan takes something on, the internet goes crazy. So apparently now you can even buy a T-shirt with that. So this is, we're really going mainstream now. So, yeah. Anyway, but hopefully you will see why this is maybe, it's a cute title, but maybe also even a little bit appropriate. So the outline of today's lecture for me is going to be, first, I'm going to tell you that labels are bad. Second, I'll tell you that data is good. See, it's going to be very easy. And third, I'm going to tell you, let's try to supervise data with data. And that's basically self-supervision. Okay? And then I'll talk about the various ways of trying to do this. Okay? So, life is good in deep land. Everybody knows this. You don't need to code anymore, apparently. The kids in high school, they don't learn Pascal or Java. They learn TensorFlow. It's true. For any given problem, you just label some data, define an objective function, train a neural network, and sell your startup, right? That's the this is the plan. But and it's like it's all these, you open up the, Facebook feed, and everyone's like, look, AI is going to take over the world. Singularity is near us. We are superhuman and doing image classification, like this, ImageNet, for example. We can even automatically caption, images. Like, for example, this is quite impressive. Look at this. A group of people posing for a picture on a ski lift. I mean, this is like scarily good, right? Singularity might be near, right? There's so much. You need to know so much to give this caption, right? So we're done. Like, why are we even here, right? Maybe we're not quite done. So I took one of those capture generating things. I put, I tried it for some of my own images. So here is an image. I put it in there and it says, a car parked by the side of the road. Fair enough. I mean, maybe like, New Zealand or UK, the wrong side, but yeah, but close enough. I give it a pass, okay? But then what I did is I got just like I typed car in Google search. I got some cars, and guess what? A car parked by the side of the road, it basically fits pretty much all of them. Almost all of them, you could say, yeah, it's a car parked by the side of the road, right? Even though these are just random images. And indeed, if I give it some kind of a little bit unusual image, for example, this, guess what? It's a car yeah. What about this one? Yep, car by the side of the road. Yeah, there is a car, there is a road, it has a side, whatever. Okay. So, and image classification, okay, yes, we have performance that is at 80%. Now, people are quoting higher numbers, but those higher numbers are, best out of 5. I don't think that's the right number to report, but still, like if the best number is like 80%, that's pretty good, right? Except if you just take an ImageNet classifier and you just, you put it in a real world, like you mount it, like self-mounted camera, and you just run it, or you just run it on some YouTube video, the performance drops to 30%. What gives? Well, the problem is that the ImageNet task is a very specific task. So my favorite example of an ImageNet category is T-shirts. So here is the T-shirt category in ImageNet, okay? And this is T-shirts in the real world, right? Right? Here's a T-shirt, here's a T-shirt, and here's a T-shirt. No wonder it's at 0% on this, right? They are so different. They're basically like, why are they even called the same English noun? They're completely different things, right? So that's why we're not doing them. And classifiers fundamentally they like to cheat. Okay, so you have this classic thing where you have your label, you have your image X, you have your label Y, and given an image, it gives you a label that says collie. And everybody's happy because that's actually the correct label, right? But how much does it actually have to work, the classifier, to do this? So one thing one could do is we can use, you guys probably heard of the Leon Gaddis's stylization algorithm that was big online for a few years ago, right? So you take the gram matrix, and then you use that to stylize it. Well, you can take the gram matrix and basically do texture synthesis. You can say, let's create another image that has the same gram matrix as this one, something like this, okay? And you pipe it through ConvNet, and it tells you the same thing, collie, okay? Now, this is not like an adversarial image. It's not really being that adversarial. It's just basically sampling texture that has the same texture statistics, okay? And yet, the network is perfectly happy to say that this is also a collie. And this is a collie. And this is a collie, right? So if you had, I don't know why you would, but if you had some hopes that somehow the classifier would be like doing figure ground, figuring out the boundary of the dog, kind of figuring out where is the dog and where is the background, where is the muzzle, where is the body. It's obviously not doing that. It's basically, there is no texture, there is no object recognition being done here at all. It's all texture recognition. It's recognizing dogginess, okay? It's recognizing dogginess, and it's fine because just recognizing dogginess will get you a long way in ImageNet classifier land, right? You have only 1,000 categories. You really only need to do, top 5. So it's not, the chance is not that high. So not that low. So you can actually, you don't need to do all the work, okay? Here is another example for action recognition. We have an input video. For example, I'm going to open the fridge. I look inside, and I close it, okay? And in computer vision, this is called action classification. You need to classify what action was just performed, right? And so you train a classifier given those frames. Which of the output labels is this, right? Is this picking up cap? Is it slicing bread? Is it opening fridge? Anyone want to venture a guess? It's opening fridge, right? And you have maybe like 20 labels. Or maybe if you're like really, really good data set, you have like 100 labels. No more than that, okay? But is the classifier actually knows that it's your opening fridge? Well, we tried to run this classifier, and we wanted to see, like, does it even need to know it's a video? Maybe you can just run it for every frame, right? And indeed, if you run it for every frame, you get the same performance. And then we can ask which frame does it actually mostly use to do this classification. And it turns out it doesn't care about any of this except this. So again, action recognition is being reduced to texture recognition. It's looking for the texture of an open fridge. It doesn't care about the hand. All of these beautiful stories that you hear in computer vision class about tracking, hand detection, affordances, opening, none of that, right? It's just looking for this. It's looking for the shelves with the texture that is shelves of stuff inside of a fridge, okay? So that's kind of set, right? And again, notice that it doesn't need to do any more because the task is so simple, this is enough, okay? And so we're breeding a generation of classifiers that is kind of like, Berkeley freshmen. They do great on the exam, but they don't quite know the material. Because they don't need to, because you can overfit on the exam and do fine, right? I mean, I've done it myself. It's fine. You just you cram the night before, and it's very hard to create exams that are very different from previous year's exams. So it's really hard task, okay? So it's going to be very similar, and so basically nearest neighbor is just going to get you there, okay? So you could say, well, what I should be doing is I should go into a Costco store and I should film a whole bunch of open fridges, right? And then it will give me negative examples for what is not an opening fridge action, right? So the open fridge shouldn't be considered an opening because it's already open, right? So I can do that, and I can add it to the data set, and then I can, it hopefully will get better. But fundamentally, I don't think that we can do this for everything, right? So, maybe a few years ago, you would have asked me the same thing. I would say, it's all, the problem is data set bias. We just need to get more data. We get more data. We need to unbias the data. And then finally, when we get enough data, everything's going to work. I'm not sure anymore. Because I think there is always going to be a way to cheat, because you always are going to have a finite number of data. The data is not going to be infinite, okay? It's going to be finite. So no matter how much data you're going to bring in, the classifiers are very clever. They'll always find a way to cheat, just like undergrads. Classifiers are just like undergrads. Very clever in all the wrong ways. So data is finite. And the thing is, frankly, this is not really something that's in the mainstream right now, because the ML people, they say that, not our problem. You're doing this crazy thing. You're testing on one distribution, training on one distribution, testing on a different distribution, right? Not our problem. It's not supposed to work, so forget it. But of course, if you want to do something real, like if I train on ImageNet, I don't want to just perform well on the test set of ImageNet. I want to do well walking down on campus, right? And that is definitely a very different distribution. So we want to work in exactly the case when the machine learning people washed their hands and said, not our problem, right? So basically, we have to deal with this, because they, on the whole, are not interested, although there's definitely some exceptions of some people who are in machine learning community who are starting to look at this problem. But it's a nasty problem. It's an ugly problem. It's a problem where you can't really say things mathematically because it's very ill-posed. Okay? And so one way I think that might be the right thing to do is to somehow, instead of assuming that you'll always just get more and more data, to try to have a better use of the data that we have. So instead of this kind of a direct supervision, which is basically just memorization. You memorize a bunch of facts that you're told, and then you hopefully do better. We need to somehow make make our computer work harder, okay? And study hard, okay? Okay? And so this is kind of a motivation for why labels are not good from the machine learning point of view. But I actually want to maybe make a little side point here, which is that it's not clear that semantics is actually even a good way to represent our world. I'm a vision person, so visual world for me, but I think it's also true in other applied disciplines like robotics. I'm not sure that using semantics, using words, using language is such a good way to represent the world, even if our classifiers didn't cheat. So let me indulge me for a bit while I kind of explain this. So the kind of one of the classic things in computer vision is semantic labels or even semantic segmentations. You give an image and you want to say what is where. You say building, sky, flag, banner, bus, face, lamp, wall, bus. Right? That's kind of a classic problem. There is a gazillion papers on this problem. And I would like to take a step back and say, is this actually even an interesting problem, or is it actually a useful problem? Because you know how they say an image is worth 1,000 words? Well, here we have about 10. In fact, we have exactly 10, right? And are they actually capturing what's in that image? Like if I gave these 10 words and their layout to an artist, do you think the artist would be able to come up to reconstruct back this? I don't think so, right? How informative are these labels to what we want to do? Not clear. Because the visual world is actually a much richer space than the world of semantic labels, the world of words. It's not a one-to-one relationship. Before I came to Berkeley, I was for a decade at CMU, and so this was my favorite example. Here is a couple of images from a couple of different places, okay, that by some fluke of the English language happen to be called the same noun. Okay, this is Pittsburgh, this is Paris. And now imagine yourself as a poor, innocent, hardworking computer classifier, and you're trying to say, well, okay, these are in the same class. They're the same category cities. So there's got to be something in common between them, right? That's the whole idea. There's some commonality within things in the same category so that my job is going to be easier. But there is absolutely nothing in common. Like, look at this. There's not a single pixel that is in common between those two things. You could say, well, both of them have buildings. But look at this. The buildings are completely different. There's just, it's functionally that we can call them buildings, but visually they're not at all the same. You can say, well, but they all have windows. The buildings have, but again, the windows look completely different, right? Everywhere, all to the finest detail, everything is actually completely different from the visual point of view. So calling them by the same noun, putting them in the same class, actually makes it much harder for the computer rather than easier. This is where I get a lot of pushback from the audience. But you guys are either agreeing or asleep.
They both have a lot of
Sky, yeah. Guess what? Everything else has a lot of sky too. Not very discriminative. Okay? And frankly, you are not going to see these beautiful clouds in Pittsburgh, yeah. But that's a different story. Okay. Yeah? Everybody buys? Yeah?
So even though the features themselves are not the same, but there's some hierarchy of organization that is very similar, right? But then there are window-like things that are organized together in a certain way, and then
even that is questionable because you have, there are patterns, but these patterns in kind of the modern buildings are actually quite different. They're much more this way rather than this way, right? So and indeed in some of the old architecture, the sizes of the windows actually change as you go. Like, you know, the more stairs you have to climb, the cheaper the rent and the smaller the windows, right? In modern buildings, we don't have that. All the windows are basically the same size. So even then, it's actually different. Okay. The same thing you say, well, nouns are problematic. But what about verbs? Well, same thing. The verb sitting, right? So here is a whole bunch of things that are all called sitting, okay? But they're very different things. And if I give you some context, then it's very easy to match between which sitting should correspond to which context, okay? Whereas this word, the verb, is basically just getting in the way. It's this bottleneck that's basically throwing away valuable information for you. It's making your problem harder rather than easier. So this is what I call the language bottleneck. You have this beautiful, you know, okay, this is a computer vision-centric talk. You can, let's say, sensory world instead of visual world, okay? You have a sensory world that's very rich and beautiful, and you know, it's noisy, but it has a lot of information. And fundamentally, most of the time, you want to do some sort of an action that is also in that real world. So in that sense, it's also the actions are also going to be noisy, high-dimensional. So why do we have to go through this bottleneck of a semantic labels in the middle, if really we're going from some kind of a high-dimensional space to another high-dimensional space, right? It seems like this might be causing us more grief than help. So in a sense, one can even go farther and say, like, why do we even have categorization? Why do we categorize, right? So this is even more like, wait a minute, this is crazy, you know. We've been categorizing since the time of the ancient Greeks. You know, why stop now? Well, this is why you guys, you know, invited me at the end of the class and not at the beginning of the semester. So, because it's like, okay, for something completely different. But hear me out. Here is why we categorize things. Well, you know, I claim that there is two reasons for categorization. Reason number one is knowledge transfer. Okay, you almost get eaten by a tiger. Okay, in the savannah, in our, you know, Pleistocene period. Okay, and then next time you see, of course, next time you see the tiger, you run away, obviously. But next time you see a tiger, it's also better to run away, right? So now you have categorized, right? You have made a category tiger so that you can survive your life in the savannah. Okay? So this knowledge transfer that you transfer from almost being eaten by tiger A to running away from tiger B. Okay? Even though it might not be exactly the same tiger. Okay? And second reason for categorization is communication. So maybe you didn't almost get killed by a tiger. Maybe it was your auntie who almost got killed by a tiger. But your auntie told you. Okay? Beware of these things called tigers. And now you know, even though you didn't actually have to have an encounter yourself. Okay? So those are kind of reasons for doing categorization. And you know, they are good reasons, but it's not clear we actually need all of them. Okay? So kind of going a little bit back in time, you know, where the way people think about categories now is, interestingly enough, not that much different from the way that the ancient Greeks have thought about categories. A lot of things that ancient Greeks came up with have evolved. Not this, interestingly. Okay? So classic view of categories dates back to Plato and Aristotle. And it postulates that categories are defined by a list of properties shared by all elements in a category. Right? Category membership is binary. Either you're a tiger or you're not a tiger. Every member of a category is equal. Okay? These are kind of the principles postulated by, by Plato, the whole Platonic notion, Platonic categories. But turns out, even though those are very natural, and in the, in the sciences we use these at least implicitly all the time, there are problems with this classical view. We humans actually don't think this way, okay? And here is some examples. A lot of them are actually examples from this very campus. People don't seem to rely on abstract definitions or even lists of shared properties. This is something that a great philosopher Wittgenstein has first argued for. His famous example is games. Okay? Think of a list of properties that are shared by all games, but none of the non-games. Okay? It's been 70 years, nobody has come up with such a list of properties. It seems to be impossible to do. The games are so different, there is nothing that you can say that's actually shared between all of them. Eleanor Roche, who is a psychologist, professor of psychology on this campus, has formulated it even further to really argue that humans aren't actually doing this kind of shared properties. And she pointed out that, the definition. She pointed out that a lot of these things that come out of the Platonic theory are actually just not true for humans. Are curtains furniture? Maybe yes, maybe no. Are olives fruit? Again, some people she actually measured. Some people say yes, some people say no. Same person could say yes today and no tomorrow. Not good. Typicality, right? This idea that everybody is an equal member of a category. So chicken is a bird, right? But when you think of a bird, you don't think chicken, right? You don't think penguin, right? You think eagle. You think, right? So not really equal. And it's language dependent. Again, a professor at Berkeley, George Lakoff, has a whole book called Women, Fire, and Dangerous Things. So Women, Fire, and Dangerous Things happens to be a category in a particular Aborigines language. Okay? All of these three things is basically one word. Like imagine your poor classifier if you just happen to have labels in that Aborigines language. Not going to be happy, but what I'm arguing is that English is equally crazy. It just that we are so used to it, we don't notice it. Okay? And the craziest thing is even by human-defined concepts. Like we define what Pluto is, we define what planet is, and still half the people cannot agree if it's a planet or not, right? Or if you're into baseball, apparently like there is all these like huge number of rules of baseball, and still you have people arguing, oh, this was a right call. No, this is not a right call, right? We are not good at this stuff. We are not good at categories. Doesn't come natural. So why are we persisting, right? You can, some people said, well, this hierarchy will solve a lot of these problems, right? So maybe we don't need to have the equal category, like 1,000 classes in ImageNet. Maybe we want to have them somehow levels of categories. We put some circles around it, and things will get better with circles. Things usually get better with circles, right? But it's still problematic, right? So you have you have this issue with intransitivity. For example, car seat is a type of chair. Chair is furniture. Is car seat furniture? No. Not good. Doesn't work. Computer go, crazy. And this is, and you actually fundamentally have multiple category membership. So there is a beautiful little blog post that I recommend to you called Ontologies Are Overrated. And kind of the argument that he makes is like, think about it like, let's say you start out a new, beautiful, file tree structure, and everything is like homework, research, papers, everything is beautiful. And then over time, it's like, well, actually, I'm going to use some of my research for a class project. What do I do? Okay, soft link. But actually, I'm going to use this paper to put into my, in my presentation, right? Things, our best intentions, beautiful, hierarchical intentions, end up being cyclic very fast, because again, this is not a natural thing. Okay. Concept space is, sometimes concept space can have boundaries. For example, in Color, there are very clear boundaries. There is, again, work out of Berkeley in the 60s that the number of colors being named, there are different names for colors. There's different number of colors in different cultures, but what constitutes a particular color is basically consistent across cultures. Okay. So sometimes categories are kind of naturally arise. But what about this? How do you categorize just a smooth gradient change? Right? It's going to be arbitrary. And there is, of course, on top of all of this, there is context, right? Where everything depends on everything else. So here is a beautiful example from Takeo Kanade. So, we have, you have a beautiful scene here. So he asks, what is this? Car. Why the hell? It's two squares here. Why is it a car? Why did you think car?
A car parked on the...
Yeah, exactly. It's because of the road. Yes, it's a car because of the road. Okay, fine. Okay, then why is this a road, right? Why is it a road? Because there is a car in it, right? It's pretty nasty here. Okay, so you can think of categorization as kind of a way of making decisions, early, right? And a natural question is like, why do we need to make them early, right? Oh, I miss one slide. So one way you can say that you can make decisions, like if you want to do the communication, if you need to communicate, if you need to have a common language, you have to decide ahead of time what's a tiger, right? But imagine that we kind of set communication aside for now. Most of the computers we have right now, we are not expecting them to do NLP, right? So if we set this aside, then the whole argument for classifying early might just go away. Okay, and it's also because we are in a digital age, the whole idea of putting stuff in one bucket also goes away. So the kind of a dictatorship of librarians. So you have you get a new book, I don't know, War and Peace, and now the librarian, you get one physical copy of the book, right, upstairs, right, and then the librarian gets to decide which shelf to put this one copy. Should be, Russian literature, war stories, love stories, really long books that nobody has read, right? So many categories, right? And they put it on one, and then it takes a while to find it because it's going to be somewhat arbitrary, right? But of course, nobody's going to do this because everybody's just going to go to Amazon and essentially create a runtime query that will find what you're looking for without the use of these categories. So Amazon actually has a button where you have all this kind of Dewey, categorization of all the books in there somewhere. Nobody even knows where that button is because nobody uses it, right? And fundamentally, we had this battle between nearest neighbors and categories. It was in the beginning of 2000s. I still remember when Yahoo was king and Google was this little upstart, and Yahoo offered to buy Google for $3 million, right? And Yahoo was employed people to create these categories, and the whole internet was basically a human-labeled set of this ontology where everything was a set of categories, and you can navigate this tree and find what you want, right? That's what Yahoo used to do. And Google said, no, forget about this. I'm just going to search, right? And we know now, how this story ends, right? The categories have lost. So,
For to each category. Right?
Exactly, exactly. So now that you can copy it, you can, and in fact, this is what some of the, have you noticed, for example, that one of those Swiss chocolates, Lindt chocolates, you go to a supermarket and you have Lindt chocolates in the chocolate section, and you also have them right out to the, next to the checkout register, right? Why? Because categories don't work, because you might want to have Lindt chocolate in a different context, right? And in fact, this is what a lot of stores do, and this is what a lot of libraries do. They buy several versions of the book, and then they put it in different shelves. Okay, but then natural question is like, why limit it to just a few shelves? Why not just have it everywhere? Why even worry about categories now that we can have infinite copies, right?
I think category will make your search faster if you want to search for a certain book. So
I think if your search is somehow language related, I agree with you. But if you're searching for something that's not related to language, I'm trying to make an argument that I think you might actually not be faster, that there's probably better ways to do the search, okay? And so this is kind of the argument that if you forget about the communication part, if you just want knowledge transfer and you just want to say that, you know, I don't want to worry about this particular tiger, I also want to worry about things that look close enough to this particular tiger. You don't need to do categorization ahead of time. You can do it afterwards. You can do essentially like a nearest neighbor thing. And indeed, this is what a great neuroscientist, Moshe Bar, he likes to call this, ask not what is this, ask what is this like? And his argument is that a lot of the reasoning that we have in our brain is not in terms of labels, not in terms of categories, but in terms of similarities to other things we have already seen. And again, in psychology, people have proposed what's called an exemplar theory of categorization, which basically goes even farther than Alan Roche, who proposed the prototype theory. Exemplar-based theory basically says we start with every instance being its own category, its own example. And then we're going to kind of do bottom-up, connections, soft connections, where things that are kind of sharing a lot of things, they will get closer to each other, okay? Hopefully should sound familiar if you talked about, deep embeddings and stuff like this. This is exactly the kind of idea that we have in that, right? And so, and kind of if we go now, a little bit of a longer interlude here, but now going back to learning, there is kind of two extremes on this learning spectrum, right? Depending on how much data you have, right? If you have little data, like zero-shot learning, one-shot learning, whatever, right? Then the problem you are trying to solve is a problem of extrapolation, okay? Generalization. You're trying to generalize from very few data. On the other extreme, you have an interpolation problem. You basically have a gazillion examples. And all you're trying to do is to find the closest example to the ones you already see. And if you have infinitely many examples, then it's very simple because you'll definitely have exactly that example in the training data somewhere, so you're done. This is why, nearest neighbor is the best classifier according to Clover and Hart, right? Because at the limit, you can do no better than nearest neighbor, okay? It's at base risk. The problem is, of course, getting the data. Yeah?
But in the context of like distribution shift that you were talking about earlier, you won't have nearest neighbors close to Lindsay's.
That's a very good point. That's a very good point, and this is why we don't just want to do nearest neighbor. Yeah, in the changing world, this does not work. And indeed, I would argue that the reason we have a brain is exactly because of this. If our environment, if our environment was constant, if our environment was static, if it didn't change, we wouldn't need a brain. We would just need a lookup table. Because we would just be doing nearest neighbor. We would just remember what happened to us and maybe our ancestors, and then we would just apply it over and over, and we would just get perfect in that particular setup. Because the environment is changing, that is not going to work. That's why we do want to kind of go toward that direction, okay? That's why we do want to do something that's smarter than just nearest neighbor. The problem is that when you ask, where do you think we are now, like in machine learning, on this spectrum? Huh?
Generalization is very little data.
That's where we are right now? Can you name one algorithm that actually does generalization? I can't. Well, I just showed you, right? ImageNet doesn't generalize at all. I think we're basically here, and some of us just don't want to admit it. Yes?
You point out over 20% for ImageNet generation to real world.
Yep.
Where is that number from?
It's a number of just running things on YouTube videos and on
Like, did anyone
where.
write a paper on that?
We should write a paper on this. I think anyone who actually tried to use that classifier for anything real will know it. I mean, yeah, it's probably a good service to actually, for somebody to actually like do a study and do it. But I think any of the practitioners know this. But it's one of those things that if you haven't tried it, you might be under the impression that it's working. Yeah. Yeah.
I felt like a lot of the problems that we've talked about are issues with trying to compress from images and vision, or sensory data, which is super high dimensional, down to words, which, as you mentioned, is a bottleneck.
That's right.
But early on in this class, we learned that if you don't have a bottleneck, it's almost easier for the model to cheat, because the bottleneck is what prevents it from just memorizing stuff. That's in like a very literal case with like literally an autoencoder, but
Yeah, yes, it's true. It's true that you can have different bottlenecks. Some bottlenecks are better than other bottlenecks. I think the problem might be both that it's a bottleneck and that there is a very few categories. So you have very few words. Okay. So if our language had huge number of words, it would be fine if it's a bottleneck, right? But because it has so few words, most people can talk in a foreign language with 500 words. You don't need that many words. It might be that this is what forces the computer to basically take cheat its way out of it. Okay. So yeah, no, it's the bottleneck itself is not the problem. I think it's the fact that it's a semantic bottleneck is the problem. Okay. Yeah.
Can you just increase, I guess, the expressivity of the bottleneck by using like longer sentences? I guess because with enough, like.
But then you run out of data, right? Because you need to have, for every class, you need to have some training data for that class.
Can I go back to the YouTube thing? Is there a YouTube data set on which people test this?
I think there is a YouTube data set. That's true. There is a YouTube data set. I'm not sure if it's labeled in the same way that ImageNet is labeled. I don't think you can just run ImageNet directly on this. But you should be able to. So yeah. Uh-huh.
Different question. There's also the results of training on ImageNet, and then the features being useful for other things.
Yes.
And that goes a little counter to the general trend of the lectures.
That is true. That is a quite impressive result. Yes, it's and that's kind of why the whole self-supervised story comes in, because when I was very surprised with when it was shown that pre-training on ImageNet was a good initialization for the features. And so the story was that I made a bet with Jitendra. This was when RCNN came out. And I said, this whole pre-training with ImageNet, I don't think you need, I think it makes sense that you need the ImageNet data. I don't think you need ImageNet labels. I don't think that that's what is really key. So we made a bet. This was 2014, that within a year there will be a method that would do as well on RCNN without pre-training on ImageNet labels. And that's basically where all of the self-supervised mumbo-jumbo, at least in computer vision, has started with, because I told everybody about this bet, that there's gelato on the line, that helped me out. And so a lot of people started writing papers, including us. And it's not quite there. We're almost at that level. It's still, we are not beating ImageNet, definitely. I have heard that I think there might be something from Abbeel now that is actually finally going to win this bet. But I think things started to be much more complicated recently, because, for example, there is a couple of papers showing that actually it looks like if your network is done well, you don't actually need to pre-train on anything. Like, there is a paper that shows that you can do RCNN without any pre-training if you kind of design your network well. So it could very well be that the reason those features are good is because the standard random initialization is just so bad that doing a little bit better than that just gets you in the right ballpark. But it's definitely an open question. This is, as I said, the argument I'm making is not an argument that is backed by data. It is a philosophical position that I admit may or may not be correct. I think it's still a useful position to make you guys aware of, because nobody else is going to tell you this. Because this is something that is a kind of contrarian view, and it may or may not be right. But I think it's good for you guys to be aware of this contrarian view, and who knows, maybe this way I can win my bet with Jitendra eventually.
What exactly needs to happen to win your bet?
Well, the bet, okay, he actually, I lost it because there was a time limit on the bet. But the bet was to be able to do as well or better on Pascal detection without pre-training with ImageNet labels. Okay? Yes?
What is the paper that says that good models don't need the pre-training of ImageNet?
I have it, so if you go to my webpage, there is a link called Academic Bets. And I have it linked from that page. Yeah. Okay, let's see what we okay, so I could do more about how great nearest neighbors are, or I can go into more recent things. You know what? Let me just show you that a lot of what we do is actually all about the data, and rather than the cleverness of the algorithm, and advertise this paper by Antonio Torralba. This is a paper that preceded ImageNet, and actually ImageNet is definitely kind of was influenced by this paper. It's unfortunately mostly forgotten, but it was a paper in 2008. They had 80 million images. So if you know CFAR10, CFAR10 is a tiny slither from this data set. I don't know why CFAR decided to take only a tiny little bit, because those are little 32 by 32 images. They could have just taken them all. But anyway, this paper, they argued that if you have enough data, magic things are going to happen. That things will just get everything is going to get close to each other. And they had everything in this paper. They had the WordNet hierarchy. they were doing all this query. And in fact, they can say, look, we can do recognition just by doing nearest neighbor, right? We just basically look at, given this image, we can look at all the nearest neighbors of this image, and then we can vote based on the word net hierarchy, or on what this is, and say, okay, entity, object, living, organism, person, scientist, chemist, ta-da! Right? And oh no, this is the ground truth, but you have, yeah, look at this. Person, skilled, yeah, maybe a chemist. Okay? Anyway, so, and you could even do things like, you can do automatic colorization by doing the nearest neighbors, right? And the cool thing is, like, if you switch the image around, it doesn't work anymore, right? Because it's data driven. It decides what color it should be by looking at nearest neighbors. Okay? So then we have some of our work here, filling in holes, blah, blah, blah. I'm going to skip that, and we can also predict GPS locations, again, using nearest neighbors. Something I did want to show that, again, is something that you don't get to see much, but it's probably one of my favorite papers of, like, the last decade, is, a lot of arguments against being against categories. It's like, well, your categories compress your data. It's too much to remember everything. Like, humans are not doing so much memorization. So there is a wonderful paper by Odd Oliver that tried to measure the visual capacity, memory capacity of humans, okay? And it's kind of supported by earlier work of Standing, which showed that if you show people 10,000 images, people will recognize 83% of those images. They will tell you if they have seen them or not, okay? And this was kind of a crazy result, right? This was quite incredible, but it wasn't clear. The images were all very different. And so it wasn't clear if people were just remembering, like, some semantics, like, oh, this is a beach, this is a bathroom, or was it more like we were really remembering details of the image? So what Odd did is she decided to kind of repeat those experiments, but also push them a little bit harder and compare not just different objects, but different exemplars of the same category, and also the same instance but in a different state. Okay? So try to make it harder. Okay? And I think the best way to demonstrate the results of this paper is to basically just have you do a little baby version of this experiment. Okay? Because that's really the only way to do it. Okay? And so while you're doing this experiment, you're going to be learning the data, but so that you don't sleep, there is another task which basically makes you click when you see something that you have seen before. Okay? So this way, what we're going to do is you're going to clap when you have seen an image that you have seen before. Okay? And this is a nice little way to relax too. Okay? Okay, ready? Okay, here we go. Very good. Okay. Okay. Okay, so I didn't make you do it for 5.5 hours, but I think you're already getting a sense of the fact, that it's actually we are doing pretty well. And so afterwards, what they did is they actually tested their memory performance, and they did it right after, and they also did it like a week afterwards. So for example, which one did you see, A or B? A. Very good. What about this?
I have no idea.
Very good, very good.
Oh, no.
Very good, very good. You see, even when you think you don't know, you actually know. Because we are just really, really good at this. So, in fact, she got better numbers than standing, 92% performance for, the same, like for different categories, right? And then, of course, the big question was, how would it do on these harder scenarios, the same exemplar or the same state, right? And so Odd always likes to ask the psychologists, what do they predict? So, is it going to be the same? Is it going to crash and burn? Or is it going to do something in the middle?
Question. We can memorize it because we pre-train, right? Because we have, because we live. So I think, what about for the baby?
Very good question. Very good question. I'll get back to this. Any predictions?
I'll say exemplar almost the same and state a lot worse.
All right. Well, now that the big boss has spoken, I think we're not going to get anything out. Nobody's going to disagree? Okay. This is the actual results. They're both actually just a tiny bit worse. Okay? Which is, of course, that was very surprising to everyone. Okay? Because you would think that, that would be quite a bit worse. So the fact is that we are very good at actually memorizing a lot of details. Going back to the pre-trained question, though, another experiment that she did that she didn't actually publish, but it's a really beautiful experiment. She did the same thing for basically random patterns. Okay? Basically, she texture synthesized images that had the same, high-level statistics as real images, but weren't real images. Guess how well people were at that task? Chance. Yeah, chance performance. So I think this is exactly right, what you are saying, that we are actually, what we are doing is we are remembering very well something that's in our embedding. Okay? The embedding, though, is much more detailed than just some category label, right? The embedding is surprisingly detailed, right? Look at this, the two different, what are they called? Remote controls, right? So we can tell the difference between those two remote controls. But still, we're embedded in a space where we can reason about those. And if we just do a random, so do we have photographic memory? No, we don't. But we have a very cool embedding that captures a lot of the information that we need, and a lot of that information is non-linguistic information, non-semantic information. It's information that is kind of a lower level. It's still there. Okay? So that result really motivated me when I first saw it, because I thought that really we need to go away from just semantics. We need to somehow force the computer to represent more stuff. Not every pixel, but more of the stuff that's important to us. Okay? So the story so far, semantic labels are bad. Cheating memorization, rigidity, loss of expressiveness. Lots of data is good, but as we said, we still want to use all that. Nearest neighbor by itself is not the greatest approach, because the world is changing. We want to be able to do low short learning, and we want to actually get to that embedding where we actually represent the things in terms of what we care about. So somehow what we want to do is we want to use all the mumbo-jumbo machine learning machinery, but go beyond just doing it on labels, on semantics. Okay? And this is where the whole argument for self-supervision comes in, right? So somehow, if we can use the supervised learning approach, the supervised learning machinery, to train the computer but use real data instead of the semantic labels for this. Okay? And that is really the kind of the motivation why we wanted to go this route. And so in my group, and this is now basically going to be just a shameless plug on the stuff that's being done in my lab, just because that's where I have the slides, is, what kind of the classic self-supervision, which is basically using data as its own supervision. What I call meta-supervision, which is kind of a self-supervision, but the idea is that what you supervise on is some function of the data, some structure of the data. So I think you guys already talked about cycle consistency. I would call this meta-supervision because it's not a supervision on the data itself, but it's on, say, I want the data to behave in a certain way. Okay? And then we can just say, you know what, the best way to avoid overfitting is to not tell the computer what the objective is. And this is the secret of evolution. Evolution is so good because it doesn't have an objective. It doesn't know what it wants to do. And so some of the stuff that we have been doing that also kind of use some of the self-supervised trick is the work on curiosity and intrinsic motivation. Okay? So now I think I'm just going to breeze through a few. So we need to get out at 8, right? So I'm going to just breeze through some of the examples of some of them. I'll try to show the stuff that you probably haven't seen because it's new, and kind of skip over the stuff that you have seen. So self-supervision, data as its own supervision. Motivation is, of course, word to vec, right? Where you have all the data, and then you just try to create a model that solves what we call a pretext task. A pretext task is a task that nobody really needs. For example, predicting the distribution of neighborhood words from a given word. Like, nobody would need this task. Why would you even want to do it? But the hope is that by doing this task, like a child playing with something, right? It's not useful in and of itself, but hopefully it will you will make you learn an embedding that will be useful for actual tasks, right? And so our kind of first attempt to do this is to basically just translate word to vec in the visual domain, right? And this was the first attempt to win the gelato, 2015. And the idea was to try to figure out the spatial location between those two patches that come from the same image. So given these two patches, where should the second patch go in relative to the first one? So let's see if you guys can do this task.
Right down.
Yes, this one. Now, let's try to, how did you do this task? Why did you think this was a correct answer? Do a little bit of introspection. There are no psychologists here, so.
Try and error. It cannot be possible at some.
But why would it not be possible? Think what is your mental process? How are you doing this?
I think it's a bus.
You say, that's a bus. Okay, so that's kind of like, I know buses. Okay, buses have that. Okay, so that goes to the top of the bus. This goes to, okay, now I know, right? Now imagine that you grew up in a world where you never seen a bus in your entire life. Never seen a single bus. Can you still do this task? No, okay? So that's the motivation. The motivation is to solve this stupid pretext task. You need to know what a bus is. So if I force you to try to learn to do this task, the hope is that as a byproduct, you will learn about buses. Because without this knowledge, you should not be able to solve this task, okay? So this is kind of the motivation for why we did this task. Because we try to force the network to learn the semantics from first principles, right? So I think you already seen this. So, we basically trained this for 5 weeks. So this Siamese net, by the way, run your networks for a long time. Even if the training loss stabilizes, just keep running. It will get better and better, I guarantee you, okay? Don't cut it after a week like some people do. including my own students, and I have to make them root. Anyway, so you train it for 5 weeks, and then you cut off one, and then you look at the embedding, and you see like what has it learned, right? And the cool thing is that now you give it this as an input, and the nearest neighbors, look at this. There are other cats. It has never been taught anything about categories. Nobody has labeled anything here. And yet, it's able to figure out a category from first principles, right? It started with the data and used context as a way to supervise grouping all these cats together in the embedding space, okay? That's exactly the kind of thing we want self-supervision to do, because it will hopefully get us to cats, but it will also hopefully get us to much more subtle kind of things that will, that will solve Odd Oliver's task. Yeah.
So it seems like before you had like 100 or 1,000 labels, and now it's just like 9, right, to solve this task.
Oh, you mean the top, in 8? The task is eight-way classification.
Yeah.
Yeah, the task is a silly task.
Yeah.
The fact that you are doing this task at random places over gazillions of images still forces you to do something. It's all about how much data and how much new data you're seeing, right? The problem with a direct thing, you have 1,000 labels, so your data is really just 1,000, it's just 1,000 things, so it's 1,000 labels, and then you have like 100 images per category, right? So that's all your data, right? Here you can have infinite data, right? Because you have infinite labels. So here, the more data you see, and by the way, even if you train on after 5 weeks, the performance is still like 40% in this very simple task. So it's not like nailing the task. It's not like ImageNet. You're done. You're 100% on the training data, right? Here it's not nowhere near because it's just very hard. Yep. It's more or less at this point it was basically like a image AlexNet clone. This was back in the AlexNet days, but yeah, it's the same amount. Mm-hmm.
Do you try the same like texture synthesis thing you did with actually learning like what the cat is as opposed to like recognizing some like statistics?
Good question. Good question. We know that it's like this. This is not. I don't think, and this is part of it. I think this is not going to really solve the Odd Oliver memory test for us exactly because it is kind of a crude task, and this is why we said, okay, you know what? Maybe we can give it more things to learn, because here we're basically getting like 1 label per image out of 8, right? So can we give it more labels per image, right? Oh, I don't have this. And this is why we did the colorization. I think you guys might have already seen this, where we did basically the same thing, but going from grayscale to color. And the idea there is that now your labels are correlated, but you have like 1 million of them per image. So you're much more efficient in your learning. You're getting or 100,000 labels at a time at every image. So the learning could be much faster. But none of this really is the reason I wanted to put this at the end was because I'm not actually happy with this stuff. I think this is very much work in progress, and the fact that we still can't beat ImageNet is to me feels like we're still not doing things right. But I think it's the right direction to work on. This is why we're not doing a startup on this. This is why this is a research topic. Yeah.
Do you have any thoughts on how the nearest neighbors look for the self-supervised features and the AlexNet features? Like, are they as good, or the AlexNet?
I have I don't have the slide here. It's not as good for some classes, and it's better for other classes. It's paying more attention to the appearance rather than the semantics. So in that sense, it's kind of trying to do better on these more subtle things in on Oliver's experiment. But as a payment, it's not matching well things that AlexNet is matching well. And actually, the interesting thing is that and we also compare it to just random features. Just do the randomly do nearest neighbors on random features. And some things, even random features, are doing extremely well on. For example, like wheels. Wheels, you don't need any training at all. It works. Okay. So it's not getting everything that AlexNet is getting, but in some cases is doing better than AlexNet. Yeah, as pre-training. Yeah, exactly. I mean, it's not supposed to beat ImageNet at ImageNet because it's not what it's trained for. But the hope is that it would beat it at Pascal, and it hasn't. It has beat ImageNet on depth estimation. So given an image, estimate the depth. You can pre-train it with ImageNet, or you can pre-train it with self-supervised stuff. Self-supervised actually does better. Actually, this particular method does better. But it's also basically it's not doing hugely better. It's like 2-3% better. So it's not like killing it.
These are patch level features, right?
Mm-hmm.
So then for a global image, you would pull these features across several patches, or
No, when we train it multiple scales. So you can think of it as being also like a full image as well.
So for Pascal, you just get the full image, you just feed it the same filters that are training on.
Well, there is a couple of layers that kind of gets it from patches to full image. But yeah.
So the nearest neighbor, the distance in nearest neighbor is just L2 distance in the embedding.
L2 or L1, I don't remember. Yeah, but it's the standard distance in like the last layer of the whatever conf5 or something. Yeah. Another motivation that actually the original we were trying to see the word self-supervision. We started using it in computer vision just because it made sense as a word. But then we tried to see, okay, who used this word first and where? And one of the earlier mentions we found is by Virginia Dessau. It's a NIPS 94 paper. And she argued for self-supervision as a way to learn things across different modalities. So you have, say, audio and you have video, and you're basically using one modality to supervise the other. Okay? And that sounds like a very powerful mechanism, because what you're doing is you have your different sensing modalities. They're going to be actually quite different, right? You sense one thing with your eyes and with your ears and with your touch. They're quite different. So they're like a perfect supervisory signal because one can help the other. Okay? And so we thought, okay, we can try to do the same thing for okay, I'm going to skip this, for representing a video representation. Because as I mentioned before, right now video representation sucks because nobody really cares about being a video. You just chop it up into frames. Single frame works fine. Worst case, you take like a bag of frames, you shuffle them around, you get the same performance. Nobody really cares about it being a video. All right? And so we wanted to see if we can use audio to push the network to actually pay attention to the temporal order of the data. And so, we wanted to somehow do it like a representation that would get both together, and we wanted to do self-supervision to supervise it. And so the idea is, okay, can we just do the stupidest thing would be, let's just learn, real matches between audio and visual versus fake. So, this is the real thing, right? And this is fake. How do we get fake? Let's take a random video and steal the audio from it. All right? That will be fake. Right? Well, the problem is, this is just way too easy. right? This is not, the network just doesn't need to do any work. It's too easy to do. So then we thought, okay, idea 2, we make it harder. And the way we make it harder is we take the same audio, but we shift it a little bit, okay? And now we get the whole temporal aspect of the problem in there. Because now, okay, sorry about some video codec issues, okay? But this is now you have to work harder. Now you actually have to not just look at the single image. You have to say, okay, there is some sort of a pattern in video, there's some pattern in audio, and they're shifted apart, so we need to have representation that can detect the shift and correct for it maybe, okay? And so that's basically what we did. It's, again, you know, whatever, 3 weeks of training, images with, videos with aligned and misaligned audio. But the cool thing is now we can actually tell, we can visualize which pixels make the sound, right? Because actually just thinking about this as a classifier, say which, you know, we can backprop back to the image and say which of the pixels are responsible for making the decision if this is a correct aligned video or a misaligned video, right? And so we can actually use this to visualize, you know, which pixels make sound. And so here is an example. It's not super accurate, but you know what. Notice that like the water waves are not being highlighted, so it's not just doing stupid, optical flow or something, right? Question. So you basically just take. It's a standard way to visualize the output of a classifier. I think a few years ago, I think the Oxford people were doing it, right? You basically you go back and see which pixels in the input are most effective for producing a particular output. Okay, does that make sense? I don't know. The task here is to say, is the video aligned with its audio or not? It's a binary classifier. And so this is a visualization of which pixels helped it the most to solve this task of aligned versus not aligned, right? And the argument is that those are the pixels that the computer needs to be watching to see if things are aligned or not, which you could argue are the pixels which are kind of, involved in making sound. Of course, when you're playing the piano, it's actually in the back of the piano is making the sound, but in a sense, your fingers hitting the keys is actually the actuators. Make sense?
So you just visualize the gradients, right?
Yeah, exactly. Yeah. Okay. And then we also thought we can use this as a pre-training to do some cute little on-screen, off-screen source separation task. So basically, and once we did it, we realized that like all these other papers are coming out at the same time because somehow the same idea everybody has at the same time. But we are the only ones that are self-supervised. But basically, the idea here is that we pre-train on our task, and then we fine-tune this network on having another self-supervised task where we basically collapse a couple of audios together with the same video, the original audio, and then some other like annoying audio that comes from somewhere else, and then the task is to separate the two, okay? And then once we fine-tune with that, so this is the input video. Okay, and this is just the on-screen. So basically, just the pixel, now it's not the pixels, but it's the sounds that have evidence in the video. Okay. And this is the opposite of that, the complement.
To show to the rest of the world the unshakable Japan-US alliance.
Okay. Now, this one is particularly easy because those speakers are different genders, but we have examples when it's the same gender and it still works. Yeah.
Can it do this like online, like as new frames come in, or does it have to look at the whole sequence at once and then split?
It does need some look ahead. Maybe 2 seconds of look ahead. Yeah, I think maybe 2 to 4 seconds. So yeah, but so do we. Okay, so do we. By the time we hear something, a couple of seconds has passed by. By the time we see something, it's already gone. We are living in the past. We are seeing things in the past. No, there's plenty of experiments to show this. There is no such thing as real time. By the time the signal arrives to V1, it's already 200 milliseconds has passed, right? And by the time we actually realize what's going on, it's like a second. So that's why humans need to predict everything because we are living in the past, so we need to kind of predict the future that would have already happened. Okay. Okay. I think I already. Do you guys see the colorization story? Okay. Yeah. So I'm going to skip that. Basically, colorization is great. You can colorize, and you can, the failures tell you that actually it's learning something semantic-y, right? Do you see that? Do you see why it's a failure? Right? It's a pink thing where the tongue should be. Why? Because ImageNet, all these dogs have their tongues out, right? So this is new. This is good news. This means it's not doing some stupid, silly, low-level image processing trick. It's actually recognizing that it's a dog, right? And indeed, we can actually doing some, deep net electrophysiology, and we can show that there are neurons that are coding for these different things, again, from just this stupid colorization task that knows nothing about semantics. Yeah?
Couldn't the argument be made the other way? Like, it's just putting pink underneath the nose rather than looking at the mouth is actually closed and not coloring it pink?
Yeah, but it knows that it's a nose. Finding a nose, that's semantics, man. that is high-level stuff. Nose detector, that's hard stuff. In fact, I don't think we can. I think eye detector is how you get a nose detector. No, finding a nose is very tricky. So yeah.
So the colors of every single pixel in an image, that's something that a human would never be able to remember.
Oh, come on. Yeah, completely. This is we're motivated by humans, but when there is a cool problem to be solved, we kind of are happy to ignore human perception. But yeah, this is totally not something that humans.
What is the right thing to predict?
Very good question. I have like 2 minutes, so let me go to a recent work that okay. I clearly have way too many self-supervised papers, but it's okay because I think most of them you guys have seen or can see. But this one I'm very excited about. Just came out, CVPR. Okay, am I even? Too many slides. Okay. What is the right thing to predict? Like, why is this carrying important information for us, this video? Because the world is smooth. The world is continuous. So you can tell that this, that, and that, it's all the same thing. It's all the same object. This does not have to be the case. There could be some crazy planet on which this is not the case, in which you're getting your frames like IID from some big distribution, and then you'll be screwed, right? But luckily on Earth, we have temporal continuity. So we should be using it, okay? And so the idea is to try to learn this correspondence using the temporal continuity as the signal. And so, how can we do this? How can we do? Well, classic thing is prediction. You can say, well, like in the stock market, you can say, I predict the stock market is going to go down, and actually it goes up, and so there's your delta, and you use this as supervisory signal, right? That's what like half of the Wall Street is doing, right? But if we have if we try to do this, like for example, Jan LeCun has been trying to do video prediction for ages and ages, and it doesn't work. It looks crappy, right? Why does it look crappy? It's not because Jan is not good. Jan is great, but it's just a very under-constrained problem, because imagine if you just had one thing going for you, like the camera would change or the object would change, right? Okay, so then you predict the space is there, and actually it went there. Okay, that's fine. You have your delta. You can train from that. But in reality, what happens is that the phase has changed, right? The phase has changed. Its position has changed. Too many things have changed, and now you're basically trying to kind of compare the present and the future, but they're not comparable. They're like apples and oranges, because it's also the appearance has changed and the position has changed. And so what we realize is what we want to do, and it's kind of the same thing as the context prediction thing I showed earlier, where what you want to do is you want your pretext task to be simple. You want it to be not some crazy, like, predict what the pixel brightnesses of the next frame are going to be. This is hard, and then you have to like regress to it and just complicate it. We need it to be simple, right? And so instead of trying to do better on this super complicated task, what we're going to do is we're going to say, you know what? We can just see if we can make a cycle, if we can go back and figure out where this patch was in the previous frame, okay? Okay, but we don't know the ground truth for that because we're unsupervised. So what we're going to do is we're going to take that same f and we're going to go it forward and say, okay, given that it's here, where would it be here? And now we have apples to apples comparison. Now we can do our self-supervisory signal, and then we can basically learn this, and then we can go back farther, make it harder, and then we get our little self-supervisory signal, and we use that signal to improve our f's, which are of course all compnets, and then we backprop those f's back, and then the representation gets better and better, and here you're going to get a better and better correspondence. So here is kind of an example of what happens like in the beginning of training, and as you train better and better, it gets better and better, okay? And then at the end you get perfect thing, and then you have your representation, and you can use this representation to do tracking, and it does pretty well. But I already am over time, so last little questions. For all the stuff I didn't get a chance to talk about, no worries, it's all on my website, but I think it was more important to get you some of the kind of the intuitions and the crazy thoughts that go through our minds in my lab, so that maybe you don't get the appreciation, but you at least get the understanding about the craziness that goes on. Okay, thank you.
Thank you, Alyosha. Awesome.
All right. Yes.
What is the equivalent Gelato set in video?
What is what?
What is the equivalent of the Gelato set in video?
With an implicit bet, I haven't put any milk-based products on it yet, but I have challenged. I haven't worked with video for 2 decades because I think it's just way too hard. But the challenge is, show me something in action recognition that you cannot do with just reshuffling of frames. Okay? So that's not really a bet on methods. I think it's more of a bet on data sets. I think the problem right now is data sets. Action recognition data sets, I think, are just way too simple. Again, because they're all semantic driven. The way you do it is you come up with a list of categories. You have, whatever, 20 Olympic sports. You make each one a category, and then you classify it. And guess what? If there is water, it's swimming. If there is water and little goalies, then it's water polo, right? If there is snow, it's skiing. You don't actually need to look at the video. So I think it's really more of a challenge to the video data set creation people to come up with a task that's hard enough that you actually need to use the temporal aspect of a video. All right? I think we go home now.